This is the 70-story Trump World Tower, the state of the art. It's designed by Ahmad Rahimian, a rising star in the new generation of structural engineers.
This building currently is the tallest residential building in the world. It has about 862 feet high. It's about 263 meters. And in order to build a building of that height, there were a lot of new technology introduced in the building.
A key innovation is how it deals with wind. It does more than just resist, it actually cancels it out. A skyscraper that sways a little in the wind may be structurally sound, but the human beings inside can quickly feel sick. This top-floor apartment is priced at $15 million. Whoever buys it expects it to stay still. To ensure this, Ahmad has installed an ingenious device. It's called a tuned mass damper. In effect, it's a huge counterweight, a massive 600-ton block of solid steel, surrounded by shock absorbers.
This element that you see here is similar to the shock absorbers that you would have in your car. However, much more powerful and sophisticated. Imagine we would have a 60-mile-an-hour wind approaching the city and the building. What you would see is that this block of mass starts moving in its own natural mode, back and forth, and as a result exciting this series of shock absorbers and dampers, which transmitting forces to the building opposite to the direction of the wind. And as a result, it would cancel the wind pressures applied to the building and suppress the building's motion.
So the evolution of structure has solved the problems of weight and wind. But structure alone was not enough to create the modern skyscraper. Two key developments in the 19th century had to come first. One was the elevator.
Suddenly, almost overnight, it became possible to move things from ground level up pretty much as high as you liked. And so people started thinking, well, maybe we could build higher if we wanted to.
With the invention of the elevator, tall buildings could reach higher than ever before. But immediately, engineers hit a problem. For all its ingenuity, Salisbury Cathedral has one fundamental flaw. Soon after the spire was added, its masonry structure began to show signs of stress.
Well, it's amazing. Above me is about 10,000 tons of cathedral, and it's piling down through this column. There are only 4 of these that hold up the whole spire, and it's got a bow in it, maybe by about 4 inches, which is slightly worrying. If I hit it, I can actually hear, it's a very high ringing sound, which means it's really stressed incredibly hard.
Since the spire was completed, it has had to have buttresses and bracing arches added to help support it. Up until the 1880s, tall building ambitions were restricted by the available material, stone and brick.
The tallest masonry building in Chicago was 16 stories tall, but the walls of that building by the time it came to the sidewalk were 6 feet thick. So architects and engineers were realizing that, notwithstanding that fact that they had elevators, the materials were causing limitations.
Then a new material revolutionized civil engineering: steel. So why did the introduction of steel make such a difference? This is a 1-meter high pier of brick. Its strength can be demonstrated by how much it can be compressed. These hydraulic rams are slowly crushing the brick. At 45 tons of pressure, the bricks begin to fail. Minutes later, they have completely collapsed. This is a steel column, the same height as the brick. The column easily passes 45 tons with no signs of stress. As the compression increases, the peeling paintwork is the first indication of strain. But it's not until 90 tons of pressure is applied that the steel begins to buckle. So steel gives twice the strength of brick, and it does it for 1/4 of the weight, which means there's much less stress on the structure. With the arrival of steel, the age of the true skyscraper could begin. In 1890, the city of New York had only 6 buildings more than 10 stories tall. By 1908, there were more than 500.
None of these buildings which you see out there would have been achievable if it wasn't because of the mass production of steel and its introduction to the construction industry.
The 20th century witnessed the rise of super tall towers. Steel was redefining man's horizons. But with great height came new problems. The huge weight of a skyscraper is carried by the steel structure. It's vital that steel keeps its strength. A fire can spell disaster.
Once you heat the steel up beyond temperatures of sort of 550 to 600 degrees C, you're starting to see significant reductions in the load-bearing capacity of that steel.
So from the early 1900s, engineers began protecting the steel structure with fire-resistant coatings. But on September the 11th, 2001, how vulnerable steel still was became tragically apparent. Yet as the world looked on in horror, many engineers watching on TV believed the Twin Towers would stay up.
And like most structural engineers, I was watching live immediately the aftermath of the planes hitting the towers, watching it while the towers were still standing there and burning.
The first thing was the sheer shock at seeing what had happened, and initially thinking that, the buildings are going to survive.
I had absolutely no idea that these towers were going to collapse into a heap in the ground.
But collapse they did. The future of the skyscraper seemed to be in ruins. Construction on skyscrapers around the world ground to a halt.
People have become obsessed with what happened on September the 11th, and understandably so. It was such a traumatic and experience and a tragedy for everybody involved. But it's hardly as if it's the first time, and it won't be the last time, that a plane has hit a skyscraper.
The events of a summer's day in 1945 over the skies of New York are now seen in a new light.
People appear to have forgotten that a B-25 bomber hit the Empire State Building only a few years after it was built.
With visibility down almost to zero, traveling at 200 miles an hour, the bomber crashed with terrific impact into the 78th and 79th floors of the building, smashing through 7 walls.
When the Empire State Building was hit, if the aircraft had struck in a different place, maybe it's slightly higher or slightly lower, you would have seen a much more serious incident there. Potentially something as serious as happened on September the 11th.
The Empire State had a lucky escape, yet engineers heeded the warning. The new super skyscrapers of the 1960s, including the World Trade Center, were designed specifically to survive an impact from a passenger jet. So why did the Twin Towers fall down?
Where you actually hit the building and how the building is damaged in the first instance, in that first impact, does have a big variance on what the overall result is going to be.
The Twin Towers withstood the initial impact, but still collapsed. In the 2 years since, Simon Lay has studied what happened intensely.
There are a lot of misconceptions about what happened on September the 11th, and most of them tend to be simplifications over what happened. It's very easy to look at World Trade Centers and say, well, a plane hit them, that's why they fell over. Or it's very easy to look at them and say there was a fire in a tall building, that's why they fell down. And really, it's actually a combination of all these different factors.
Severe structural damage combined with a fire which was spread rapidly by burning aviation fuel proved too much for the Twin Towers. After 9/11, engineers are now using sophisticated new computer simulations to examine how fire attacks an entire steel structure.
We've effectively simulated either an aircraft impact, for example, or a bomb blast in this part of the building. So you can work out how heat actually penetrates that particular piece of structure, and then you can work out how long it's going to take before the structure gets hot enough to actually fall down.
Structural engineers are absorbing the lessons of September the 11th. They're designing skyscrapers to survive much longer by adding more of what's known as redundancy. It means building a structure to hold together even when part of it has been destroyed.
We've looked at making absolutely certain that the building will survive until the last person has got out of the building. We can't allow people living or working in these buildings to be so vulnerable to an event like September the 11th.
So the goal is to design a skyscraper to survive even when the unthinkable happens. In 100 years, skyscrapers have leapt from 10-story brick to 100-story steel. All of a skyscraper's weight is eventually transferred down to the ground. This ultimately takes the strain